Welcome students. Here I am back once again with a chemistry class about oxygen. So oxygen has a symbol O and formula O2 having atomic weight 16, density 1.42 gram per liter at STP and solubility 14.6 milliliter per liter of solvent at 0 degree centigrade. One common allotrope of oxygen is ozone, that is O3, mostly found in the upper atmosphere called the ozonosphere, and oxygen has three isotopes having mass numbers 16, 17 and 18. In this class we will focus on these topics as you can see on your screen. First discussion will be about the laboratory and the industrial preparation of oxygen, followed by some physical properties, chemical properties and few uses relating to oxygen. So let us focus on its laboratory preparation first. Well, laboratory purposes require few liters of oxygen which can be prepared either at room temperature or by applying heat, as you can see in the table. Room temperature methods can be done either by decomposing hydrogen peroxide or sodium peroxide, and we will discuss both the methods in brief. And heating method will require potassium chlorate to decompose. First, let us see how hydrogen peroxide yields oxygen. This process is called catalytic decomposition of hydrogen peroxide. Hydrogen peroxide decomposes quickly in presence of catalyst manganese oxide or manganese dioxide to form oxygen. For this purpose, hydrogen peroxide is dropped from a dropping funnel at manganese oxide kept at a conical flux, as you can see in the diagram. Oxygen thus produced is collected as depicted in the picture by the downward displacement of water. The chemical reaction in this connection is given below. Let us now see the catalytic decomposition of sodium peroxide. The procedure is almost the same. Solid sodium peroxide mixed with manganese oxide is kept at a conical flux over which water is dropped in the form of droplet from a dropping funnel. Oxygen thus produced is collected by downward displacement of water. The chemical reaction in this connection is as shown in the bottom, as sodium peroxide decomposes to form oxygen and sodium hydroxide. Let this time see how decomposition of potassium chlorate is brought about by the heating method. Well, potassium chlorate and manganese oxide is kept in a hard glass test tube. On heating around 250 degrees centigrade, potassium chlorate starts decomposing to produce oxygen, and again oxygen is collected by the downward displacement of water, and you can also check out the chemical reaction in connection with that. In all the processes discussed earlier, manganese dioxide or manganese oxide acts as catalyst. It accelerates the decomposition of peroxides, and in the case of potassium chlorate in the heating method, the yielding of oxygen is made feasible at much lower temperature. Let us now see the industrial method of oxygen production. Unlike in laboratory, industry requires tons of liters of oxygen, and one of the handy methods to produce such a huge amount of oxygen is the electrolysis of water. Hydrochloric acid in this case may be taken as electrolyte. Dissolution into ions are in the form as shown in the picture. Hydrochloric acid produces hydrogen ion and chloride ion, and also dissociates water into hydrogen ion and hydroxyl ion. Hydrogen ion, being the only cation, reduces itself at the cathode by taking electron and thus eventually producing hydrogen gas. And amongst the anions, hydroxyl ion has more tendency to oxidize itself than the chloride ion, and hence reaches the anode to shed electrons. Ultimately, oxygen is produced and is collected inside an inverted test tube placed right above the anode. Among the physical properties, some have already been discussed early in this video, and among the others, here are some. For example, oxygen is colorless, odorless gas, slightly heavier than air, and that's the reason why each time it has been collected by the downward displacement of water. Let us now quickly make a tour over the wide range of chemical properties exhibited by oxygen. Well, oxygen is highly reactive and ranks second in electronegativity after fluorine and followed by nitrogen. It even directly reacts with all the noble metals and even with the inert gases also. Let us now discuss briefly what the oxides are. Well, they are binary compounds, that is, compounds comprised of two elements, one of which is oxygen. Take for example sodium oxide, calcium oxide, water, etc. Oxides are broadly categorized into 5 categories as shown in the picture, and they are acidic oxides, basic oxides, amphoteric oxides, peroxides, and neutral oxide. Discussing briefly the acidic oxide varieties. Oxygen on reaction with nonmetals forms non-metallic oxides which are called acidic oxide. Let us see for example oxygen reacting with carbon, a non-metal, to form carbon dioxide, and another non-metal is phosphorus to form phosphorus pentoxide, and also sulfur to form sulfur dioxide. These oxides, carbon dioxide, phosphorus pentoxide, sulfur dioxides, are all called acidic oxide. Now the very question strikes in the mind why they are called acidic oxides. To find the suitability of such a nomenclature, we have to go one step further. Adding water with these non-metallic oxides results in production of acids. For example, the aqueous solution of carbon dioxide is carbonic acid, and that of sulfur dioxide is sulfurous acid, and that of phosphorus pentoxide is phosphoric acid. Again, you can see sulfur dioxide can further be oxidized to sulfur trioxide, which upon dissolution into water produces sulfuric acid, and thus the nomenclature holds good. Let us now see what the basic oxides are all about. Basic oxides are formed when oxygen reacts with metals. Take for example sodium, calcium, and potassium among the metals. Sodium produces sodium oxide, calcium producing calcium oxide, and potassium produces potassium oxide upon reaction with oxygen. Then again the very question strikes in the mind why they are called basic oxide. Well, it is found that the aqueous solution of these basic oxides are alkaline in property. For example, the aqueous solution of sodium oxide is sodium hydroxide, and alkali, and that of the calcium oxide is calcium hydroxide, and that of the potassium oxide is potassium hydroxide. Both are alkalis. Thus the name holds good in this case also. Let us now discuss what are amphoteric oxides all about. Well, they are oxides which show both acidity and basicity. It means that amphoteric oxides upon reaction with acid form salt and water, and again that same amphoteric oxide upon reaction with base or alkali produces salt and water, and thus that amphoteric oxide showing both acidity or basicity. Take the example of aluminum oxide as amphoteric oxide, which while reacting with acids such as hydrochloric acid produces aluminum chloride, which is a salt, and water as depicted in the reaction. Again, the very oxide, that is aluminum oxide, while reacting with alkalis such as sodium hydroxide produces salt named sodium aluminate and water. Let us now very briefly discuss about the peroxides. The peroxides must have peroxo or peroxide bond as shown in the picture. And if we analyze the structural formula of hydrogen peroxide or sodium peroxide, the very existence of this peroxo bond is seen inside them. Let us now discuss about the neutral oxides. Water is the perfect example of such oxide, showing a neutrality that is neither acidic nor alkaline. It has a pH value of 7, which is considered to be a landmark separator of acidic and basic property. Let us now briefly discuss some other properties of oxygen. Well, oxygen is highly electronegative, that is, it has a high affinity towards electrons. It grabs 2 electrons to form oxide ion and thus reduces itself. Oxygen is said to be a good oxidizing agent as it reduces itself that is, it oxidizes others. Let us now see a special property called adsorption. Yes, you have heard it right. Adsorption, not absorption. This is actually absorption of oxygen in the outer surfaces of some metals like platinum, palladium or silver at room temperature. Oxygen gets back into the atmosphere upon hitting these substances very easily. Coming towards the end of our tour, let us now discuss some of the identification reaction of oxygen. There are several identification reaction of oxygen, and we are to discuss the first of the alkaline solution of potassium pyrogallol. Well, the alkaline solution of potassium pyrogallol is colorless, which upon absorption of oxygen turns into brown as shown in the figure. So this is one of the identification reaction of oxygen. In the second identification method, oxygen turns colorless solution of cuprous chloride into blue, what you can see in the second picture. Let us now see how oxygen evolved in the atmosphere. Initially, atmosphere was not conducive to life as oxygen was very scarce about 350 billion years ago. Then life was in the form of anaerobic bacteria or microbes which didn't require oxygen to live. Then cyanobacteria came into existence. They analyzed seawater in presence of sunlight to produce huge amount of oxygen. These cyanobacteria can be seen in the croplands even in these days also. Gradually, green algae, phytoplankton came into existence, which were enabled to perform photosynthesis, and the amount of oxygen began to surge. Oxygen now make up about 21% of our atmosphere, and almost all living cells require oxygen to burn food inside them and to maintain life. Dear students, all the topics that have been discussed so far in this video can be found in your textbook in elaborated manner. And that's all for now. Thanks for listening and watching.